I'd like to introduce Patrice Brissette, who will be presenting exploring SONiC's integration of EVPN-VxLAN. Patrice is a distinguished engineer from Cisco Systems and traveled from Ottawa, Canada, and joined us today. This is Patrice's first time presenting at NANOG, and it's a pleasure to have him with us. Let's welcome Patrice.
Hi. Hi, everyone. How's it going? So I'm Patrice Brissette. I'm a distinguished engineer at Cisco, but also workers on the SONiC front. So I'm leading the SONiC Routing Workgroup as well. So if somebody wants to contribute, join us, join the force, so we can develop that SONiC environment. So before I start, I just have a question for you. Who knows about SONiC in the room? Okay, who work on SONiC in the room? All right, you guys I know in the back. You can. All right, okay, thanks. So let's see. So the agenda will be split in two parts. We're gonna talk first about SONiC itself, quick overview in the architecture. So I want to make sure everyone's on the same page to start with, and then the EVPN-VxLAN, the development we've done lately. I know it's an old technology, but you know, SONiC is still at the early stage, and we need to bring all the good features on it. So SONiC. So what are the goals of SONiC? Well, it's all about disaggregation, right? And I think the belief in the community is that we can develop a faster technology than any other NAS or any other company developing their own NAS. We also try to, one of the objectives is to reduce the operational burden and also to use any silicon under the hood. And also obviously to be fully open, right? So whenever you're developing your feature, just upstream it, get the community to help out, testing, debating. All right, so also if you believe that there's not much traction, this is pretty much all the companies that are really sponsoring SONiC. So I will not go through it. Okay, you can take a picture. Probably, most likely your company is already there. The screen is divided into the silicon and platform adoption, but most of the main contributors are spanning across all of those silos. So the journey started in 2016 with very basic switching operation. And then over time, the routing was added, okay? And more feature were brought from community until like late 2000, like the 2020s, where EVPN, the control plane, and BGP start to be start to work on it. And then we finally got EVPN-VxLAN out. So now we have a full IP fabric using BGP. Underlay, overlay, you can do multi-tenancy with VxLAN, and we're also supporting already now the multi-homing aspect. So SONiC, the architecture is quite simple, but quite difficult at the same time. So as you can see here, there are, I guess, like 4 or 5 major pieces. The first one is the routing stack. The routing stack is what we are using is the FR routing. So it's basically the BGP, Zebra, and other little friends there, but the full routing stack is over there. There's a lot of other containers that I'm going to show you later, but also another big masterpiece there is the kernel. The Linux kernel is in the middle, sits in the middle. It's mainly used for slow path support, but it does also a lot of protocols. I like it, I don't like it, I don't know. You will see it later. We're going to go through it during the presentation. And then there's really the SONiC pieces at the bottom, where you will see more the database, the interaction between the orchestrator of those information coming from top and how we program the ASIC through the SI API. There's a common SI. Some companies use also their own side or private side, but at the end, works quite well. So this is like the overall setup. Now, the next slide is this one. It's a little bit more crowded. I took it straight from the SONiC doc website. So if you go there, the beauty is you can read for hours and it will explain you all the main flows, how to bring a port, how to boot up a router and stuff like that. But if you look at the architecture, everything is based on container. So at the top, it's pretty much all the application. And where you see BGP container this is the FR routing. This is where the routing stack is as a control plane. So you will have the BGP, obviously, the Zebra, which is kind of a rib, but at the same time, it's more than a rib, but it's less than a rib. It has like EVPN stuff will be part of this. It's kind of a melting pot, but you can see it more as really a rib right now. And then there's you can see underneath there's the FPM SyncD. That's one of the two channels that we are, or one of the two channels that we are using to send the data up to the SWSS, the SONiC part at the bottom. And then as part of the SONiC, what we consider really SONiC, the SWSS container with all the agents are. And then you have your Redis server right in the middle for everything coming in, coming out. The database container are meant for configuration, state, and etc. There's many purpose, and we'll see it through those slides as well. One thing you will notice, it is always like a SyncD it's kind of an agent for messaging for a specific purpose, okay? And for a SyncD, most likely in the ARC agent, you will have an agent doing the processing of the data coming from that SyncD. So each time you have a database doing a purpose, most likely you have a SyncD and you're gonna have an agent into the ARC agent doing the work for that. That's a bit the golden rules which is being followed. So therefore, it's kind of very easy to browse the code, because if you're doing an operation on the ports, well, most of these will be something a port SyncD, and probably like a ARC agent, you know, inside, or ARC arch, we call it, inside the ARC agent. So the code is quite well structured for that. It doesn't mean it's well done, but at least it's doing a good job. So everything is a container, so therefore you can load or upload or boot any container as you want. If you don't want to use the FR routing stack, you don't load the BGP container. You can use something else, right? And then the kernel again is in there, obviously. So yeah. All right, so let's move on. So now let's look at so that was like just quick overview of the SONiC. If you have more questions on the architecture, we can always discuss afterwards, right? But at least you have a bit of foundation why we are now going where I'm going with the EVPN-VxLAN. So EVPN-VxLAN, the concept, it's really based on the old goodies that most likely all of you knows if you have worked on VxLAN in the past. So basically, the way it's being built up as a concept and with the construct is you have always a bridge domain for facing your access. And then that bridge domain will have an L2VNI for your stretch. Then you have your SVI/IRB for people who knows better the term. And then it will have an IP address that will bring you to your VRF. So therefore you can do L2, L3, but the VRF is not enough because VxLAN, as you know, impose an Ethernet header on top. So therefore you need to go through another SVI to another BD, and then you have the L3VNI to do your routing. So when VxLAN has been brought by the community on SONiC, all of those blocks has been designed and added. So you will see it if you go through the code. But there's no surprise. I mean, it's really VxLAN 101, but there's no cheating here. And then what we added recently is the entire multi-homing for like what is in blue in the middle, like at the bottom, everything which is the synchronization of ARP and the MAC address, the support of ESIs. So if you look here, the left part of this slide is what was there. like what was brought since 2020, and what we did lately is the right side, where we brought completely the redundancy. So for sure, we are using symmetric IRB. We are not doing asymmetric right now. We do static unicast gateway. So again, the design is meant for data center, okay, for small data center. So if you have like more complex use case, we need to talk, because we are really straightforward on the type of design for IP fabric. Obviously, we added also the mobility aspect for everything which is MAC and host. Duplicate address detection, and name it. There's a lot of features around that are required for VXLAN to work. So this is this slide is like, well, the layout of the slide, you will see it everywhere. So I try to reuse it all the time to facilitate your understanding. So let's start with the inclusive multicast. And as you can see, I brought back the major pieces I was showing you earlier. So there's the FR routing, which is the control plane, the stack, right? Your routing stack. So that's why I put BGPD, the Zebra, and sometimes the FPM channel, which is being used on that. Then as part of the SONiC itself, you will have the SWSS, and as part of the USS, you have the SING-D we talked, and also the ARC agent. And then you have, on the right side, I put all the database, the Radius database that are being used. Just quick parenthesis for people who doesn't know, but FR routing is a separate community. So therefore, if you go to SONiC routing, it's not FR. FR has its own bubble, right? It's its own entity. So just be aware of that. So this is why sometimes people are getting confused about SONiC. Oh, FR is SONiC. No, it's two community, but one is using the other one. So anyway, so you have more question on that, we can talk about it later. So, all right, so now for the multicast, for the inclusive multicast, so each time you're receiving a route type 3 from EVPN, the way they did it is they are trying to reuse a bit of the channels going through the kernel. So they are providing like a route, like a MAC route, with a VTEP and NextHop information through the kernel. So it goes through FDB SING-D. I don't know why they did that, but anyway, that's how this is right now. And then it goes to AppDB. AppDB is like kind of the catch-all database for everything coming from north, basically. So once it goes there, they will get a notification will be given to VXLAN Arch, who's gonna take the data, chew it, remaster, and start setting up the tunnels, right? So therefore, you will have all the tunnel with the remote NextHop being set up. So therefore, you can start doing your ingress application towards the remote VTAPs that you have. So there's no like concept of multicast download. It's via really those fake MAC route where they are adding the VTAP. Also, any routes that we are receiving when we are bringing the system up, like for the bridge, or let's say route type 2s, or route type 1s, or route type 3, each time the new VTAP is showing up, this is getting exercised because it means, oh, there's a new VTAP coming up somewhere, first in, first come, then I can set up my ingress replication list so I can start doing multicast with it. So that's the principle that was there. So in terms of unicast, only for the MAC, well, you can either get the local MAC or the remote MAC. So for the local MAC, it's quite simple. The ASIC DB, well, you learn it in the hardware, it goes to the ASIC DB. The ASIC DB will give it back to the FDB Arch. And then it goes to the state DB, because the state DB is like if you want to know in what type of operation your router is doing or the SONiC is doing, that's where you need to look at. And from there, it goes to FDB SING-D, FDB for MAC, okay? So that's why you have your FDB Arch, again, I keep repeating. And then it will go through the kernel, and the kernel up to Zebra, BGP, and then it gets advertised as a route type 2. So now, for BGP point of view, whenever you get a remote MAC, it's just the reverse way. But again, instead of going through state DBs, because it's coming from north, you go to AppDB, notification happens, and then we program the ASIC. So what is interesting here is everything goes through the kernel, as you can see. So netlink message are heavily used with all the benefit and the problems that come with it. So we're going to cover that a bit later. Now, if you look at the MAC IP, just the host itself, right? The route type 2, but fully L2, L3 together. Again, similarly, actually I find my slide very boring because it's always the same flow. But we're just switching it, the SYNC-D to be, instead of being the FDB, now is the neighbor SYNC-D and the neighbor ORG who's going to do the operation. But at the end, it's the same thing. However, what we do in SONiC is all the ARP and D goes directly through the kernel whenever we learn it. So therefore, this is why also earlier that you saw that the MAC is going through the kernel as well, because you need to complete your adjacency. So the adjacency itself is not enough to know if you're completely bound or not. So therefore, the MAC goes there, your adjacency got resolved, and then you can give it to 0. So for the IP prefix, purely L3, okay, this is where it's getting more interesting. As you can see here, there's an update going to the kernel, obviously, but the reason is more for slow path support or for ping or for, you know, those little protocols to work. But now you see the FPM channel is start to being used. And this is where it's kind of interesting because you don't need to add more burden on the kernel and the net links and all the problems that comes with it. So that channel, that FPM channel goes straight to FPM sync D again, because it's like data, goes to AppDB as usual, and then the route ARC agent will take care of processing the data. Now, what is kind of interesting is when you get the route, there's a lot of information that comes with it, right? Your remote next hop, your VTEP, so all the information to be able to perform your encapsulation. All of that happens within the route ARC agent because it was going to talk to the VERF ARC, the VxLAN ARC, and then it can create or manipulate and expand all the structure that the ASIC DB is expecting to receive. So therefore, whenever it applies to the SI, well, then it works, you know. So this is kind of a very cool design, I find it, because you don't have the kernel in your way, right? And it makes life very simple because it's all under the control of few ARC agent. Now, in terms of multi-homing, all right. So again, so there's way more information, or there's a lot of information that we added recently to be able to achieve the functionality. And they are listed here. As you can see, there's a lot of stuff going to the kernel, but not all of them is going through it. So why we download the kernel? You just want to keep it honest. The slow path support is there. There's few protocols being done by the kernel, like the ARP and the DHCP. By the way, it's a different container. I was showing it earlier in the previous slide, so it's not performed by the kernel. But at least if your ARP and D is being processed, that's good. If you can do ping, that's good. If you can do trace route, that's good. So a lot of information is being pushed, but it's a single direction. Whereas the rest, again, what we are doing, we are using the FPM channel. And with the FPM channel, then FPM channel is more under control. You can bulk, you can do, you can play with it. Actually, it's a channel which is being designed by us. You don't need to go through yet another community, which is the Linux kernel. Because if you want to change something in the Linux kernel or in the netlink, well, then you need to go to the Linux kernel community. It's up to you if you want to go down that route, but it's not perhaps the easiest one, where with the FPM channel, it's under the SONiC control, and we can optimize it, you can prioritize the message on it, you can bulk it, you can do, well, you know, whatever it's required to achieve your convergence, scalability, and functionality. So as you can see here, there's a lot of information as I was saying, but with multi-homing, there's all the whole thing is about DF addiction, split horizon groups and labels, well, labels, VNIs. But all of that information needs to be given to the SONiC side from the FR routing. So therefore, what is happening? It goes to the app.db, right? So you're gonna update the split horizon table, the DF, the backup next up to do fast reroute, all the forwarding, tunneling required. Your L2 next up group also is going all of there. So now you can, and inside the ARC agent, there's a lot of agents doing different work. Remember what I said earlier, usually there's one agent for your table or table/database or table that we are doing. So therefore, everything which is related to multi-homing, like your DF election table, who is or the priority, or your preference of who's going to win or who's going to lose, all of that has been processed by the EVPN, Multihome, the first one in the list. The FDB, I keep it there because FDB is everything about the MAC. The L2 next subgroup is how do you resolve those MAC. So because now we have, if you have all active multi-homing, then I'm gonna have a CMP. If I'm the remote router, I can do a CMP across peering leaves. So therefore, I need a next subgroup that's gonna have a list, so I can do a CMP based on hashing. So this whole next subgroup is maintained by the third guy in the list. Also, you need to do split horizon list. Why? Because each time you're doing BOM replication, you need to filter back in, and you need to break the loops, right, for your flooding. That's the guy who's going to be doing it. And, well, obviously, because the feature is about VxLAN, you need to touch that VxLAN arch. But again, it's always, as you can see, the flow is always pretty much the same. So obviously, we needed to add the local bias. I think there's nothing new here for people who know EVPN, multi-homing, local bias, how to break the loops for BOM traffic. This is the algorithm that was implemented. Is the same everywhere. If you look at any, I guess, NAS by any provider in the world supporting it, that's what they do. So basically, whenever you're in a multi-homing scenario and you have your peer leaves, you need to learn the VTEPs where they are sitting, right? So you're gonna see them coming based on the route type 4, and now you can say, oh, this is and you can build a list of partners. And whenever you're sending and you're flooding and you're getting a flood packet, well, you just look at your source VTEP and say, oh, is he from one of my partners or not? And if it's coming from one of your partners, then you can decide to drop the packet. If not, you can let it go. So, and the local bias, what it means also is each time you're doing your replication, you always replicate locally. You don't need to do that. But anything coming from the network or for the fabric, you need to check, and you need to do that type of check to see, is it going through or not, right? So sometimes also, if you're getting packages from a remote guy, well, first of all, you look at that, you look at the source VTEP and say, oh, it's not part of my list. Well, it's just like, it's not because it's a remote guy. So it's like considered as a single home, so none of that is applicable. So again, really, really basic VxLAN stuff here that was developed. So now, if we look at the challenges, what are the challenges that we got over time? Well, first of all, FR routing did not design the VxLAN aspect, EVPN/EVPN, 5 years ago. A lot of assumptions were made at that time, which are no longer assumptions that can be true. So therefore, it was highly challenging just to understand what was designed, but even worse, why some of those decisions were made at that time. Because you look at the code, or you're trying to you simulate the entire environment, and many things that whenever you want to expand to support multi-homing did not make sense. So there was one of the biggest problems, not having the history. The second thing also is everything about mobility. So I think people does not understand what mobility means. So we fixed that up, but it took a long time. And mobility, it's very simple because you need to design for seamless motion. So if you can do seamless motion with host mobility, you cover them up. But I think what was done there was not that. It was more just a sub piece of it. So again, not having a history and all of that were the main challenges. Now, the biggest one was the guy in the middle, the kernel. So I was explaining to a friend of mine this morning one of the main, like some of the issue, okay? And whenever you're talking to the kernel, you're using netlinks message. And with the netlinks message, well then, it's kind of funny because you're updating the kernel and its state. And each time the kernel state is getting updated, well, it will reflect back that state to all the consumer listening to the kernel. And when it does that, it's giving a status update using a multicast message. Because it's multicast, it doesn't use, like if you look within the netlink message, the PID, the process ID is 0 because it's multicast. So you need to understand that to start with, okay? So now, what happens is whenever you're in multi-homing and you start synchronizing your MAC, well, you're getting a MAC from route type 2 and you say, oh, I need to program it locally. So then you program the MAC coming from BGP, you program it locally into the kernel, so it goes to the SONiC and you set it up. And what does the kernel do? It says, oh, I got a new state. Send back the message to everybody, all the consumer, and say, hey, I got a MAC. So Zebra got a MAC and say, oh, you learned it locally. Oh shit, I need to advertise it. So you advertise it. It goes to the other side. The other side got a route from BGP and say, oh, I need to install a MAC. So you install it the kernel, and the kernel, what it does? Well, it tells everyone, hey, I learned a MAC. And then you start bouncing. So I created a huge storm of MAC the first time I set that up, because I didn't know that. And I teared down the engineering network for 2 days. And they were very happy on me. So therefore, now what I can tell you is, with FR routing, we set up Ubuntu or Colima for Mac, and you can run FR routing on your Mac only, right? Inside a VM, you can do all of that testing. If you crash, you only crash your own computer or just a VM, and people are fine with you. So that's why also that if you want to start contributing with us on that, well, you can do all your work on your Mac. You don't need an internet connection, Wi-Fi, whatever, so it's pretty cool. So it's kind of funny what I just show you as a quick example, but there's a lot of problem like that with the kernel that you're not expecting. So therefore, to fix that, it's quite simple. I just open up the Linux kernel, and I add the protocol field extensions, and the protocol extension already existed for layer 3, sorry, but did not exist for the bridge forwarding database and the VXLAN forwarding database. So I just added that. And what it does is you can set up who is the source of the message, because we're kind of using the kernel for messaging at the same time than updating the forwarding state, so the adjacency is happy. But yeah, so protocol extension, you set it to Zebra, so whenever you're sending down your message to the kernel, bounce back in your face, say, oh, protocol is Zebra, it's myself, kill it. Simple like that. So yeah. The other things also that you need to be aware is the Linux, like the way FR was developed with the Linux kernel is, well, they are using the Linux kernel to hold the state of a Mac. It's kind of a good idea and not a good idea. Anyway, so if you have a hardware platform like we do that is doing his own Mac learning, you will punt once the Mac to software, goes to the kernel. The kernel will say, oh, I learned a Mac, cool. And then we'll give it to Zebra, you advertise it in BGP like usually, but the problem is that Mac is owned by the kernel. Guess what? It will age out. So and it will age out, but it will age out in not the way you're thinking a hardware is gonna age out, because usually it's 5 minutes, it's gone. No. You will put it into stale, and then you will have a garbage collector coming that later on that will connect all the Mac and may remove them if you're going across some thresholds and etc. You know, so it's quite a journey to make it work that way. So what we decided to do, and what the community approved, is that we are gonna go completely away from that mode. So you're just passing through. So learn it, it's externally learned. Kernel learn it because I want to make sure that your adjacencies are happy and complete. But the rest, you're not managing it. It's being managed by the hardware. Give it to Zebra and see you later. That's it. Don't age out, don't do anything about it. Just take it as cash. So that's what we did. It works very well, actually. And this is one of the updates that we're going to provide to the community. But now, saying that, this is where there's another problem with that MAC handling. So what we did is the left side of this picture. Now you do that, okay, obviously whenever you do this type of solution of multi-homing is not only for redundancy, but it's also for convergence, right? So if there's a failure among your access link, you want to reroute as fast as you can. To be able to achieve that, you need to maintain you need to maintain the states of your MAC. So you can have like, well, actually the source of it, basically. So you can have like the control plane and the data plane learning the MAC. Because I can learn it locally, but the peer leaf can also learn it on his side and synchronize it via BGP to me. So now I know that my MAC can be local or pointing to my best friend right here, you know. So therefore you have two states. And in our hardware in SWSS, we also implemented two states. But our friend in the middle, which is the kernel, doesn't have two states. It has only a single state. So how do you do that? Well, you can just pass through it, but the problem is whenever, let's say your hardware, your SONiC side, has the control plane and has the data plane knowledge that there's two sources, and let's say your MAC is aging out locally, well, you need to tell Zebra about it. So what are you going to do? You're going to send a delete. I don't have it. Well, and then Zebra will say, oh, you don't have it, cool. But the kernel doesn't have it anymore neither, because it's a single source. So what you need to do? Well, you need to talk again to the kernel, say, oh, no, hold on. It's still there. It's just like so therefore you have all of those bouncing, right? It's there, not there, there, not there. Just because you need to, the messaging is going through that little tiny pipe in the middle. So it works, well, until it doesn't work, right? So therefore, what are we going to be doing? We've been talking about it quite a lot, and so we're going to follow exactly how L3 is working. If you remember the IP route I show you, where it goes straight to FPM and goes down, and you just update the kernel for making the ping or the slow path support working, we're going to do the same thing with the MAC. So I think it's going to create a good achievement, because now you don't have that problem of single source. You don't have a problem of playing with the kernel, saying, oh, you need to be externally learned, don't age out, don't do all that crap. So all of that will be gone. And also with the FPM channel, well, because it's under our control, we can design it perhaps to be better with bulking or having a better prioritization on, okay, I don't know, there's a reroute happening for a route, there's a MAC also being there, which one I prioritize, perhaps I'll prioritize the route so I can do, my L3 is not broken while the other guy can keep flooding. You know, you can do all of those prioritization on message and make it very, very nice. So you can achieve scalability, and you can achieve most likely a much better convergence. So I can keep going on and on the kernel, but I think we'll go to the next one. There's a lot of problems. So now, here is more like a slides that I want you to think of, because see, once you have multi-homing developed, well, we developed it for, well, what I was showing you earlier, the VxLAN L2, L3, you know, but also you can see it very differently. And that's what I want to bring your attention to, because see, why do we need an L3 VNI to point to a verve? You can just do it in a verve, right? Or you can just do it in a global. And if you do it in a verve, you can use an L3 VNI, but I don't need a fake BD. I don't need that Ethernet port, right? So therefore, there's people in the community developing L3 VNI as an interface. So therefore, it's going to help us to avoid all of those funny things in your data plane where you need to go a couple of BDs so you can optimize it, have a better pipeline. Most likely has more throughput at the end, you know? So this is the left side of it. But then also is like, why do we need to do always L2? So if you have a very simple IP fabric where you don't need stretches or you don't need mobility, like L2 mobility or L2 transparency, you can just do it like the right side of this picture is showing you, because the only thing that you need to do is synchronize your tables. So synchronize your ARP, synchronize your neighbor database, synchronize your MAC. So all the adjacencies facing your access are fine, and you're done. So this is why I call it as a service. It's really cool that as part of the FR routing and the stack, we are going towards that direction. So we will enable a lot of different scenario for the IP fabric, but also make it more simple to use as well. So in terms of usability, so this is what you need to configure. And SONiC, the way we are doing it is it's kind of also an umbrella, or it's taking over the kind of the FR routing as well, because as I was showing you earlier, it's a container. FR routing is just one container as part of the SONiC. So therefore, the entire config is not owned by the container itself, is owned by the OS or the environment, which is the SONiC side, okay? So therefore, whenever you want to configure your L2, your VXLAN, you will do this type of configuration. Again, it's just like some screenshot. I don't think it's by far complete, but at least it gives you an idea. What will that do is it will also go and talk to Zebra, talk to the right container, talk to the kernel, because you still need to create all the construct for slow path support, but it's all done under the hood. What is interesting is the BGP aspect still remain like that, right? So the bottom part, when I say FR routing, we still go on the side and set up BGP manually. So we are kind of in the middle of the two, right? At some point, I hope it's going to all be on one side, but anyway. So and the BGP, it's really kind of simple. If you go on the FR routing website, you have all the documentation. It's very well done. All the commands are very well explained. So yeah. So yeah, but just be aware that there are always two aspects of it. So if you look at the L3 VNI, it's a bit the same thing. So again, you need to create all the construct I was showing you earlier, like here. So all of those modules, right? Like the SVI, the BD, all of that needs to be construct. So therefore, whenever I see the L3 VNI, then it's the same thing, right? You have this long list of commands on the SONiC side that will go through the proper container, the kernel, set up the forwarding chain, and then you're good, you're up and running. And again, like I explained before, from the BGP side, from sometimes the Zebra side, there's few commands that are still specific under FR, not being taken care yet by the SONiC side, so you need to do the twos. So I think that's what I have to present today. Any questions?
Hi, Logan Blythe. What was it like getting all of this merged into upstream SONiC? Because you talk about the kernel, and the kernel has its own process, and so I was just kind of wondering what you thought about getting this into upstream SONiC.
Okay, that's a good question. So the question is about when are we going to upstream down, right?
Yeah.
All right. So okay. So at Cisco and as many other contributors, what we are doing is, first of all, there are kind of two steps on that. There's, well, the HLD is already out there. It has been approved, has been discussed with the community. The community is happy. So that has been upstream already. Okay. From a PR point of view, is as we go. So most of them, okay. So we are not building that for fun, by the way. So we have customer on it. So by contract, we need to upstream, and we have dates to, targeting and all that. So there's a lot of work happening also behind the scenes, because see, We can open, like, let's say if you open like 35 PR, who is in the community will have time tomorrow morning to review this? No one, right? Because you have your work, I have my work, he has his work. I mean, so there's a lot of conversation that needs, and sponsoring, say, guys, I need your help. And then it's kind of a, you know, I'm helping you, you're helping me, and all that. So that's how that's going to work. So it will take times, obviously, but it's like that for everything. So. Well, the kernel actually, honestly speaking, I thought I would have got beaten there when I added the protocol support, and actually they were kind of very, very happy to see this happening. They say, oh, it was a miss, so we need to... Actually, that one is my easiest side. FR routing is a bit different because they are not following the same process. See, in SONiC, you must have an HLD, you must have the SPI test, you must have the you must add the test to the SONiC management framework before you can upstream. FR has different rules, so you need the topo test, you need other stuff. So it's and also is how many PRs, how big is our PRs, and who you want to partner with so you can get those reviews happening. That's the challenge, actually. But I think that's the challenge for any open source community. Sorry.
Hey,
hello.
Thanks for the presentation. So my name is Prabhakar from Siena. How is memory management done in SONiC, specifically the container memory? Like every time we introduce a new container, how much memory is allocated to that particular container? How is that decided?
I have no clue. I have no clue. I don't know. I don't know. I don't know the answer.
No worries.
We can talk about it. I can find out, but I have no clue.
Sure. Second one, is there any front-end validation that takes place for all the configuration, or it's directly sent to the Redis subsequent?
No, there's oh shoot. Okay, so that's a good one. It always depends on the application at the top, to be honest. Because see, if you look at the hold on. Okay, DHCP, right? There's now a DHCP container for that. Well, obviously, they will manage their own configuration. If they are happy with it, then it will send out via most likely messaging to FPM SyncD perhaps, or whatever SyncD they're gonna create, and then they put it in the AppDB. So the application is kind of responsible about what you can do, what you cannot do. Same thing with FR routing. You cannot just configure whatever. There's validation happening, obviously, because otherwise, just the stack will not work on its own.
Okay, thank you.
But let's talk about the other one that I don't know. Sure. That's a good question. Hello.
Steve Ulrich, Next Top. Just a quick question at the end there. You mentioned there were FRR components. Is there plans to upstream or provide support for unified config mode with the associated FRR components?
Don't know.
Okay, thanks.
Sorry. Don't know. Unified configuration? I don't know.
Any more questions in the room? Do we have any question in the remote?
So if everyone has or want to talk about it, I'll be free after, so no worries.
Okay, I guess that. Thank you for your wonderful presentation. Yeah, that was very informative.